All right, I'd like to take the next 20 minutes or so and go over last year's exam. Solutions are posted on Blackboard. But take a look when you get a chance, and this will hopefully answer any questions you have. So we first start with the 4 conceptual questions. They're only worth 5. When looking at any of my tests, you'll have conceptual questions that are worth the same. They're each worth 5 points, and then you'll look here, and it doesn't matter how difficult each one of these are. They're each worth 20 points. So look at the whole test. Okay, I'll say that first. So projectiles 1 and 2 are launched over level ground at different speeds. Both reach the same height, which hits the ground first. There's a couple different ways to look at this, but the clue is they reach the same height. In order to do that with a constant acceleration of g, they're going to hit the ground at the same time. So C is the correct answer. Acceleration due to gravity on Jupiter is about 2.5 times what it is on Earth. If an object is thrown vertically upward on Jupiter, how many times higher or lower would it go on Earth? So I left you some wiggle room depending on how you answer this. But if we just look at v squared equals v naught squared plus 2a y minus y naught. Sorry, I'm getting used to a new pen. So we look at this kinematic equation. This is just a one-dimensional problem here. At the maximum height, that's going to be true. So that y final would be some h. We'll call y initial 0. So your height is going to come out to be v naught squared over 2a. So the way I did this, just to keep track of things, and you can reason through it differently, but the height on Jupiter divided by the height on Earth, that would be the same speed. So I'll just use v naught squared over 2. And on Jupiter, it's not going to be g, it's going to be 2.5 g. And then on Earth, it'll just be v naught squared over 2g. So the g cancels, the v naught squareds both cancel, and we end up with 1 over 2.5. I know you can get to this ratio discussion a lot faster than this. By the way, this is 40%, 0.4. So it goes to 40% the height, however you want to say it. The figure below shows a position versus time for a moving object. Consider the positive direction to the right. At which directions are the following true? Moving to the right, or yeah, the first one, sorry, the object's turning around. Well, turning around would be the location where the velocity is going from positive to negative or negative to positive, right? That takes place when something's turning around. Well, that's happening at E, right? The slope of this plot is changing from its positive, 0, negative. So the object turned around there. Moving from left to right, so that would mean a positive velocity, right? Moving to the right, we define the right as a positive direction. So it would be anywhere on this plot where I have a positive slope. So it would be B, C, and D. Here the slope 0, here the slope 0, here the slope's negative. So we're good. The object is speeding up. This one's a little more difficult. I had some grace on this one. If you look at B, we're going from 0 to a positive velocity, and then it goes a constant velocity, and then it slows down. Then it has a negative velocity where it's speeding up. So at B and F, it's speeding up. At B, it's getting more positive. At F, it's getting more negative. But in both instances, the word speeding up works correctly. They're just in different directions. And then figure below shows 3 points on a steadily rotating wheel. Rank the speeds. Well, for each one of them, we talked about the period will be the same, right? So the period is the same for each of these. And the speed will be the circumference that it goes around, of the circle it goes around, divided by the period. And they're all going to share the same period. So really, we just need to look at radii. So the speed at 3 is going to be greater than the speed at 1, which is the same as the speed at 2. Okay, this is kind of like a conceptual version of that mountain climber problem on your homework. All right, well, I have got my camera there. I think it puts it over to the side whenever I record, so I can't read this problem. I'm gonna have to read it from my notes. fresh off the printer. Leaving home, a man walks 1,000 meters north and 1,000 meters east. His speed is 1.5 meters during his entire walk. What is his total displacement? He turns around and walks home in a straight line. How fast must he walk so that his journey home takes the same amount of time as his journey outward? All right, so this is just really playing around with our definitions of velocity and displacement. So, I mean, I've got to draw a picture. So the first displacement is north. I'll call that D1. The second displacement is east. I'll call that D2. And then this is the direction he's going to walk to get home. And my notes, I called this D home. Sorry, my handwriting's so bad. I just got a new pen for this, and it takes a minute to get used to it. So what is his total displacement? Well, this is one of those instances like I talked about in class today. His total displacement is just going to be the sum of these. So there's a lot of different ways you can write this. He went so much in the north and so much in the east. So we could write this as 1,000 meters and 1,000 meters in bracket notation, right? This would be positive is the way we're talking about it. I didn't include these, but you could also write 1,000 meters x hat plus 1,000 meters y hat. That's a correct way. But when I ask for just the displacement, you can tell me in a lot of ways. Or you can give the magnitude. I guess I should have put a total here. The magnitude is going to be 1,000 meters squared plus 1,000 meters squared. Take the square root, which I should have been able to do that. I shouldn't have looked at my notes. 1,414 meters would be the magnitude. I mean, it's 45 degrees north of east, however you want to say that. You could do the trig, or you could look at the fact that if you do this and an equal amount do this, you've got a 45, 45, 90 triangle. So if he wants to walk back home, we've got to think about this a little differently. So let's think about the total distance he traveled. So he traveled 2,000 meters at 1.5 meters per second. So that means his time out to walk outwards is going to be 2,000 meters divided by 1.5 meters per second, or 1,333 seconds. So that's how long it took him to walk that distance, right? In order to take the same amount of time to get home, well, to get home, he has to walk this magnitude, which is 1,414 meters. So his speed home is going to be the distance he walks home, which is 1,414 meters, divided by the same amount of time it took for him to walk out, because that was the stipulation of the problem. And he needs to walk 1.06 meters per second. Does the answer make sense? Yeah, he's covering a shorter distance, right? The hypotenuse is going to be shorter than the sum of the lengths. So it makes sense that if he wants to do it in the same amount of time, he gets to walk slower because he's going a shorter distance. Now, this is probably the quickest of the four problems. This or possibly number 6, worth the same points though. So look through the entire test, because you know what? You can feel really unsure about the test, but get to a point where you're like, cool, I have 40 points. Now let me do the conceptual questions. Cool. I feel confident about 3 of those. I have a 55. Now let's start working on the other ones, right? Think about it like that and realize that we all depend on partial credit when we work physics problems. All right, you're driving at night at 20 meters per second when a deer steps into the road 35 meters in front of you. Your reaction time before stepping on the brake is 0.5 seconds, and you can brake at 10 meters per second squared. How much distance is between you and the deer when you come to a stop? So we need to draw this out, right? This is another scenario. It's very similar to a lot of the homework problems we worked. It's a scenario where we need to draw out the picture because we're going to have some accelerations change. So if I define this position as 0 meters, the deer is over here at 35. All right. So for a certain period of time, my acceleration is 0. And then at this location, to say where I stop, my acceleration is going to be negative 10 meters per second. All right, so I kind of could tell the story there. Oh, sorry, I scrolled on accident. All right, this is me cruising along for that half a second, not changing my speed at all. So I start out here at 20 meters per second. And you know what? Right here, I'm still going 20 meters per second because I still haven't stepped on my brake yet. And we have enough to really solve this problem, but like all of these problems, we really have to step through. I have to know where I am when I start slamming on the brakes. Then that's going to be my initial position as I'm slamming on the brakes. And then I need to figure out, where am I here? What is this? And I called it 2. So what I did is I labeled this X3. I called this X1 and this X0. All right, just to keep everything nice and separated out. All right, so let's find out where I am traveling at a constant speed for half a second, right? That's pretty straightforward. And this is even one that if you think about it, you can do in your head, but let's lean on some kinematic equations. X1 is going to be X0 plus V0, I'll just call it V0, and we've got T. This T, did I label it? Let's label it T1, because it's time that gets us to location 1. And we have no acceleration, so I'm not going to write the other term. It's just going to be 20 meters per second multiplied by a half a second, or 10 meters. So now I know that I don't have 10 meters to stop. I have 25 meters to stop, right? So kind of start the problem over again. And I need to find X2. So this is really what I'm looking for. Let's keep my eye on the prize. What else do I know? I know my acceleration. I don't know how long I'm braking, so I don't know time. I know that I'm stopping. So I know right here, I'll call it V2. V2 is 0. I know V1 is this value here, right? The velocity didn't change between 0 and 1, location 0 and 1. So I don't know time, so I'm gonna go here first. V2 squared is V1 squared plus 2a X2 minus X1. I know everything there except for X2. I'll skip some. If you want to see the algebra, it's in my solutions. X2 is going to be X1 minus V2 squared over 2A1. Comes out to 30 meters. It's fine. Sorry, I was counting signs, and it actually does work out. So honestly, on the test, if you got to here, and I understand there's some nerves involved when tests are taken, and sometimes I remember last year some people said 30 meters, I'm at 30 meters, I'm done with the problem. Really, you're 5 meters away from the deer, which is what the question was. But you were basically there. I'm not going to count off over little things like that. All right, the next problem is, once again, my ugly mug's in the way, at least on my screen. A magnetic field, which we'll learn about next semester, can force a charged particle to move in a circular path. An electron moving in a circle experiences a centripetal acceleration, so we're given that, of 3 times 10 to the 14th meters per second squared. Little particle can handle a lot of accelerations. We're good. What is the speed of the electron if the radius, so we're given the radius, is 0.15 meters or 15 centimeters? So really, this was a bit of a give me. So centripetal acceleration is v squared over r. So that means v is going to be the square root of the centripetal acceleration multiplied by the radius. You were given the centripetal acceleration and the radius. So you get a speed of 6.7 times 10 to the 6 meters per second. Then you're asked about the period. Well, if you remember, the speed is the circumference of the circle that's being created in the circular motion divided by the period. The period, just by definition, is the time to go around once. So from here, t is 2 pi r over v, which is 1.4 times 10 to the negative 7 seconds. All of this happens very quickly. Just want to remind you, because I've never graded one of your exams before, and I want you to know, say, I mean, this is A, this is B, I equally weight them. If you get this wrong, if you get A wrong, but use it correctly in B, I'm going to give you full credit for B, right? It's about how you use the values. It's not always about exactly the values you get. All right, and this is the problem that this was much less than a 10-minute problem. This was maybe borderline a 10-minute problem, and this one was less. I consider this one as maybe going a little bit over, so I wanted to give some cushion just to give you an idea of how I wrote the test. I'm 75 meters away from my friend holding a target at the same level that he is holding his airsoft rifle. So this is safe. We're going to prove that if I drop the target at the same time he shoots the gun, he'll hit the target. All right, we talked about that in class, right? They fall at the same rate as being dropped, right? It depends on what the initial velocity is in the vertical direction. They both have a initial velocity in the vertical direction of 0. The problem in this situation is that I wait 0.2 seconds after he shoots to drop. We're given the muzzle velocity of his airsoft rifle. By how much does he miss the target? And then I also say, don't try this at all. So really, we need to keep track of 2 objects. We worked a problem today where we talked about a bullet falling. We were given the distance that it fell over some certain distance with a certain muzzle velocity. We had to find the muzzle velocity. Here, we know the muzzle velocity. He's holding the airsoft rifle horizontally, so there's no angular component. So we need to find how much that bullet falls, right? To find that, we have to find the time that it's allowed to fall, right? The airsoft bullet is going to fall while it's in the air. We need to know how much time it's in the air. So we need to find the time, and then we'll find how much the bullet fell. Well, then I know that the target fell for 0.2 seconds less. So how far did it fall? The difference between those two will be how much I missed the target. So first, I'm going to find how much time is the bullet in the air. So bullet time, not the matrix version. So what do I know? I know it travels 75 meters in a given amount of time. I know that it has no acceleration in the x direction. So x is equal to x naught plus v naught xt. Or, sorry, I know v naught x is 200 meters per second. T is going to be x minus x naught over v naught x, or 75 meters divided by 200 meters per second, which is 0.375 seconds. So that's how far that's how much time the bullet had in the air. I'm just going to write a little note over here. The target has 0.2 seconds less than that. So it's only going to fall for that long. I'm just going to go ahead and note that. I don't think I did that in my notes. I think I just referred back to it. But the time of the target is going to be 0.2 seconds less. And I can just then find, in that amount of time, how much did the bullet fall? Right? How much did it get accelerated at its speed down? How much did it translate in the vertical direction? And then the same thing for the target. So bullet y displacement will be y equals y naught plus v naught yt plus 1/2 a sub y t squared. I didn't draw a picture here. I mean, really, it would be, let's draw a big O target. It's all lined up and it falls like this, and then the target's going to fall some. I like drawing big targets though. I'm automatically doing this. I'm going to consider that I get a negative value. So the acceleration in the y direction is negative g. If we look through, if I call this initial 0 and it's aimed horizontally, so this is 0. How much I'm off is 1/2 negative g T of the bullet that I found squared. Plugging that in, I get that it fell. Sorry, I lost my negative. Negative 0.689 meters. It fell a lot. That's a slow, fairly slow bullet over 75 meters, right? It's 3/4 of a football field almost. All right, so this is where the bullet is. Now let's find out where the target. We'll find the target Y displacement. We're really just going to do the same thing. Y of the target is Y naught of the target plus V naught Y of the target. All right, I'll just put T's on all of these, I guess. I guess I was using capital T. Let me be consistent. Plus 1/2 A sub Y T squared. All right, once again, I dropped the target, so the velocity in the Y direction is 0. We called that height 0 anyways. So this is going to be 1/2 negative G multiplied by the time of the target squared, which we've already determined to be 0.175 seconds. That gives us negative 0.15 meters. So they're off by, there's lots of different ways you can answer this. Negative 0.539 meters. Some people just gave me 0.539 meters by just taking the difference between these two, taking the absolute value. You missed the target by 54 centimeters. It is true, though, that if they fall at the same time, they fall at the same rate. So if you aim directly on, they would hit. So that was last year's test. Probably this was the most involved problem, I think. Possibly this one. I don't remember huge glaring mistakes or anywhere anybody went wrong. But I mean, think about what we covered over the last couple weeks, right? We've covered a discussion of displacement, velocity, and acceleration. And I hope you understand that. We've discussed one-dimensional motion, which is here, a little bit here. We discussed two-dimensional motion, which would be this kind of projectile motion problem, and we're still working those problems in class. And we discussed circular motion. So circular motion will just kind of come up every once in a while, but it'll always be a special topic until we get to a discussion of rotation in late October. Hope this was helpful for you, and take care.